Welcome to the course on small wind power generation. For familiarization with small wind power generation technology, mini-wind, it is basically necessary to explore three areas of knowledge. 1. Wind technology, and more specifically, the particularities of the small power range. Secondly, the characterization of the wind resource, the source from which wind power comes. And third, finally, the possible uses, that is, different systems where a small wind turbine can be connected. And of course, all this will be focused on the Latin American and Caribbean area. The energy that can be extracted from the wind is the kinetic energy contained in the airstream. Depending on the shape of the obstacle opposing the wind, different aerodynamic situations may arise. Airfoils seek to optimize these situations so that the yield will be maximum and loads on the blades minimum. Of the total power contained in wind, the maximum that can be exploited is a value that is known as the Betz limit, in memory of the German researcher. In order to characterize the aerodynamic efficiency of wind turbines, the power coefficient is defined as the ratio between the power supplied by the wind turbine into the axis of rotation with respect to the power contained in the incident wind on the rotor. The fundamental characteristic of wind turbines as regards energy characterization is called the wind turbine power curve, which is a function of the electric power supplied and the incident wind speed. Three zones can be defined from left to right, from the lowest to highest wind speed. 1. The zone in which there is enough wind speed to allow generation. Secondly, the zone in which the wind turbine tries to capture the maximum power from the wind. And finally, the zone in which the wind turbine regulates the power output. The values that define the ranges in this categorization have been chosen from the norms that affect small wind turbines. The value of 40 square meters is the range that is currently expected for integration in the urban environment. The limit of 200 square meters includes most applications of small wind turbines. Finally, the limit of 100 kilowatts is defined in some countries as the maximum power that can be connected to low-voltage electric grids. The pico wind range is commonly accepted for less than 1 kilowatt wind turbines. Let us now look at an analysis of the technological solutions adopted in the design of small-power wind turbines for each of the subsystems, exploring the most commonly used options with the models on the current market, and comparing them with the solutions used on large wind turbines, which are almost always different. A first classification of turbines can be performed according to the layout of the axis of rotation of the wind rotor, thus distinguishing horizontal axis and vertical axis wind turbines. However, there are other classification criteria displayed on the slide, where the most common options have also been highlighted within each classification criterion. Horizontal axis rotors are characterized because they turn their blades in a plane perpendicular to the incident wind direction, while in vertical axis rotors, rotation occurs in a plane parallel to that direction. Most small wind turbines are horizontal axis, but it is true that in recent years, models of vertical axis turbines have proliferated due to their application in urban environments, where they may have certain advantages with respect to the horizontal axis type. Turbines can be designed so that they work in the upwind configuration, when the rotor is in front of the tower, or the downwind one, when the rotor is behind it. Most wind turbines on the market are upwind horizontal axis wind turbines, although the number of downwind turbines is growing in new designs aimed at integration into urban areas. Most designs of small turbines use a direct connection between the rotor of the wind turbine and the electrical generator, without any gearbox, although some designs with a two-stage gearbox have been reported. In nearly all the designs, very small wind turbines, that is, less than 3 kilowatts, use a permanent magnet generator, or a PMG. In the case of wind turbines in the range of 3 to 30 kilowatts, in addition to the PMG choice, induction generations are used. There is a wide variety of solutions used to regulate power and speed in small wind turbines. Some of them are shown on the slide. The elements commonly used to achieve this electronic control may include the regulator or charge controller and inverter. Three-phase AC output is usually converted to DC power, a conversion that is performed by an electronic converter called a rectifier. Once we have DC power, mainly two modes of electronic regulation are available on the market. Finally, the inverters convert DC power to AC. The normative aspects of mini-wind installations affect both the connections of wind turbines to small isolated generation systems and the interconnection with the conventional electricity grid. Although there are certainly very few existing standards specifically concerning mini-wind devices, there are many norms which directly or indirectly affect this form of power generation. The activity has mainly been developed in two areas: the International Electrotechnical Commission and the International Energy Agency. To end this technological section, some of the experiences gained in Latin America and the Caribbean are shown in what refers to the manufacture of small wind turbines. In addition to the distribution of models from well-known international manufacturers of small wind turbines, there are also local manufacturers in this particular region. This slide shows some of the makers present in the region. Without aiming to be exhaustive, the information can be considered to be representative of existing activity. Speed frequency distribution is obtained from measurements carried out on site. With this information, a histogram is drawn up with the occurrences of each interval. The shape of this histogram can be approximated by a wind speed density function, and the most common ones are Rayleigh and, above all, Weibull, characterized by the shape parameter k and the scale parameter c. The main factors that affect the characterization of the wind resource are wind shear and the variation in wind speed with height, mainly due to the friction of airflow with the Earth's surface. Then we have the windrows, which is the most widely used representation of the directional distribution of the winds, which represents the percentage of time that the wind comes from a certain direction. Finally, we have the altitude of the site chosen, which affects the density of the air. As we all know, this decreases with altitude. Fortunately, during the past few years, there are increasingly more regions and countries that have maps of this type. Thus, for example, Argentina, Bolivia, Brazil, Chile, Cuba, Mexico, Peru, and Uruguay have wind maps, both national and regional. Existing maps are different, both in the way in which they have been developed and in the information they provide. However, they are certainly a step forward against the situation of not having any information at all about the wind resource at the site to be analyzed. The characterization of the wind resource is very different in systems with very small wind turbines of typically less than 10 kilowatts power, and in those with larger wind turbines within the range of mini-wind generation. In the case of the smaller wind turbines, characterization is carried out almost exclusively in the exploration stage, omitting the rest of the stages and focusing on the calculation of the theoretical energy production of a wind turbine on the site. The energy produced by a particular wind turbine, characterized by a power curve, at a particular site, characterized by a wind speed density function, is obtained by multiplying, first and for each wind speed, both values, and second by adding up all the results. The result is the average energy produced, which is a parameter that characterizes the energy generated by a wind turbine on a given site. Small wind turbines are mainly used in two areas. First, we have autonomous systems, also called isolated or unconnected to the grid. These are not connected to any large grid and are therefore responsible themselves for controlling the voltage and frequency of the system. Then there are distributed generation systems made up of small generators connected to large electric grids, where there is an operator of the system who is responsible for the general control. This application is frequently called connection to the grid. In grid-connected systems with mini wind power, often there is no other component in addition to the wind turbine, apart from protection and counters. In isolated systems using mini-wind technology, the situation is different, the components that can be part of an isolated system being the ones shown on the slide. The wind turbine has already been described extensively in previous sections, so the rest of the components will be described in less depth. If we examine isolated systems using renewable energy, in general, we would have to include other forms of generation, photovoltaic generation being the main one. Until today, the most commonly used renewable technology in isolated systems has been photovoltaic, and all the evidence suggests that this trend will be maintained and will even increase in the future. In addition to photovoltaic generation, another form of generation is very attractive in isolated generation systems, that is, microhydro generation. In small power systems, the controls are as simple as possible with a view to cost reduction. As the size of the system becomes larger, more sophisticated control systems must be introduced. Optimization of the operation involves the selection of the best combination of components to achieve a balance in the flow of energy, fulfilling some targets in advance and respecting the limits and restrictions imposed by the operation of the system. Among others, the storage technologies available feature electrochemical systems, including all types of batteries, both traditional, lead-acid, and advanced. Then there are electromechanical systems. These are kinetic storage systems based on conventional flywheels made of steel or advanced materials manufactured with composites. There is also energy through water storage systems, pumping water up to a certain height for use when power is required. In isolated applications, generators are the classical form of electrical power. With proper maintenance and use, these systems are very reliable. Their basic drawbacks are the replacement of fuel and preventive maintenance. Generators have traditionally been seen as the competition to renewable energy, but another perspective is possible. That is, seeing generations as an identifier of a market for renewable energy, a job that is indeed not always easy. The calculation of consumption is the first task to be performed when dealing with the design of an isolated hybrid system. This is the major component of the system influencing the design. It is essential to calculate consumption as accurately as possible so that the design will adhere to subsequent use as much as possible. The first point to be underscored regarding the consumption of an isolated system is energy efficiency. In previous sections, the following configurations of systems have been identified with mini-wind, and we shall now look at them further. Thus we have grid-connected systems and isolated systems, among which are systems able to store electrical energy, wind diesel systems, and systems with neither electrical storage nor genset. The most common mini-wind grid connected configuration is shown in the figure. The components have already been described in the reference to mini-wind technology. From a technical point of view, the electrical connection of mini-wind does not represent any greater complication than the adjustment of the parameters of the inverter with those of the grid. The situation from a regulatory and an administrative point of view is very different, because the situation depends largely on the site where the installation is to be made. In these systems, batteries play a fundamental role. Apart from their evident role as energy storage systems, they also act as voltage regulation systems. The other components, wind turbines and/or photovoltaic generations, are adapted to the voltage imposed by the energy balance at the battery terminals. The presence of wind and photovoltaic controllers is explained by the need to protect batteries against overcharging, while protection against over-discharging would be a function of the inverter. In such systems, the grid is initially established by starting the diesel engine. Once started, the grid is set and loads can be connected. Once this has been done, the overall control of the system can allow the wind turbine control to connect when it considers this appropriate. But what if the wind power is greater than the load power? In this case, we encounter the need to dump loads, whether useless or typically useful as pumping or water desalination systems. Therefore, these are systems whose most valuable result is often not electricity itself, but some other product that can be stored easily and inexpensively. Heat or cold, and water. Desalinated or purified water, ice, water in reservoirs, etc., are typically stored products. For each of these configurations, it is necessary to discuss the peculiarities of the components involved, as well as some of the most typical applications that use them. Experiences with each configuration will be addressed equally for the Latin American and Caribbean region. One of the opportunities provided by this configuration is the elimination of long-term electrical energy storage systems, that is, batteries, by providing the grid with both power stability and storage capacity. Also, it is usual that the wind turbine controls themselves, that is, rectifier plus controller plus inverter, are sufficient for the proper functioning of the system, not requiring supervision. The application of small wind turbines connected to the grid in urban environments has great potential. Let us look at some peculiarities. Normally, the energies involved in a hybrid system will be photovoltaic and wind power, with microhydro to a lesser extent. Most isolated wind energy power systems have used lead-acid batteries as storage systems. The complexity of the control depends on the size and complexity of the system, and of course, the preferences of the customer. Here we see a simplified proposal for a hybrid isolated systems design broken down into 3 stages. The presentation was given by countries, highlighting the following projects. First, Argentina. This is surely the most active country in the area regarding this technology. Chile. This includes the study of systems of generation with wind and diesel for 10 islands in the archipelago of Chiloé. In Peru, we have 20 hybrid systems, wind power 100 watts, 50 watts, 5 volts, already deployed in the former rural electrification plan. It has been estimated that there are 3,500 homes that might potentially include mini-wind systems on a reliable basis. Then we have the Eurosolar project. Proposed systems are isolated systems, most of them fed only with photovoltaic generation, although there are 177 systems that employ PV wind hybrid systems. Other forms of renewable generation involve photovoltaic or microhydro supports, but these are not frequent. Looking at storage, this can be short-term, such as with flywheels. With respect to control, The types of supervision have different complexities depending on the level of wind penetration. Regarding generators, these of course are essential since they are part of the actual functioning of the system. With respect to consumption, this should include deferrable loads to make the system more efficient. Here we have two examples for the Latin American and Caribbean region: the wind diesel system of San Cristobal, the Galapagos Islands, Ecuador, and Nazareth project in Colombia. Within the peculiarities of these systems, we see the following. The storage is a product derived from electricity generation, and no electrical energy is stored. Control is essential but simple. The generator may exist but is not essential. Regarding consumption, this is deferrable with no dedicated loads.